In section 10.3, hopefully you've got that outlined. One of the first big ideas from 10.3 was your coefficient of determination and non-determination. Coefficient of determination, if you looked it up, it's a little lowercase r squared. So the same symbol as our correlation coefficient, but now it's squared. What it actually represents is your explained variation divided by your total variation. You might be thinking, oh, Miss Golly, so that doesn't make much sense. So let's actually see what this means. So let's find it for our example, and then let's put into words. Let's do the explaining part. What does that coefficient of determination mean for us? Easiest way to find it, again, it's just that little lowercase r squared. Our correlation coefficient, take it and square it. We found that last time in example B, part B I should say, and we found that to be 0.861. So again, this is from part B, same data as last time, same example, we're just continuing on with our number of assists and our total points. So we go ahead and we take that value and we square it, and we roughly come up with 0.741. Now typically our coefficient of determination is written as a percent. And let's explain what that actually means. It means that 74.1% of the variation in the total number of points, which was our dependent variable, so the total variation, so 74.1% of the variation in the total number of points is due to the variation in the number of assists, which was our independent variable. So the variation in our dependent variable, 74.1% of it is due to the variation in our independent variable, which was our number of assists. How else you could phrase that, instead of saying is due to, you could say accounted for by the variation in whatever our independent variable was. You could also say can be explained by the linear relationship between assists and total points. So several ways you can phrase it. You're not even limited to these. These are just 3 different options for us. When you're talking about can be explained by the linear relationship between assists and total points, we're taking a look at now that linear regression equation, that linear regression line that we drew. So you can use any of those explanations you would like. The second piece of this, it says the coefficient of non-determination. Super easy to find. It's just 1 minus the coefficient of determination. So super easy to find. Both of these are super easy to find. The explanation for this one, again, we want to write it as a percent. 25.9% of the variation cannot be explained by the variation of assists. Or in other words, 25.9% of our variation is simply due to chance. Our second big idea is our standard error of the estimate. That's our standard deviation of our observed y values about the predicted, those y prime values that we get from our linear regression equation. How it's denoted, we still have that little lowercase s that has been signifying our sample standard deviation for our means for quite a while. But now we add in, to show its standard error of the estimate, there's a little EST subscript on it. The formula for it isn't too bad. It's the summation of, we take all of our y values minus the predicted y values, which would be denoted those y primes. That quantity is squared, divided by our degrees of freedom, which remember, n minus 2. N minus 2 this time. I know we had to switch gears. We're very used to n minus 1, but now we're switching gears, n minus 2. Easiest way to get the numerator. I'll show you a little table you can draw up, and then yes, I will show you how the calculator can do this for you. But I know some of you like to use the formula straight out, and that's okay. I'll show both ways. The first two columns of the table are just your x and y values that you originally had in the beginning of the question. You typically, if you're thinking, oh, that table looks like a lot of work, you would not have to. If you were doing this as a textbook question or a test question, you wouldn't have to recopy down all of these values. Again, these values, I'm just getting them from the beginning of the question. The next piece you come across are the y prime values. Those are what we get from our regression equation. So when we put in our specific x value, what would we predict using our regression equation? What would we predict that y value would be? I still have all this information entered into my calculator from when we did this example. If you didn't, don't panic. You can re-enter it in now if you want to. But I just want to show you a couple easy ways to get those y prime values. You can get them very quick, very easy. Make sure your regression equation is in your y1. If it's not still there, that's okay. Just follow along with what I'm doing up here. Couple places, couple options for you to get those y primes. You can go to your graph, and you have your regression equation graph there. Just go to second, trace, it'll give you your calculate menu, and we just want to calculate a value. We just want number 1. Then what you can proceed to do is enter in, my first x value is 26. I press enter, it gives me the matching y value. 29 is my next one. Press enter, it gives me my matching y value. So you could go through and do that for each x value. Other option for you, second graph will give you your table. So you could arrow through your table and just get the specific x values you need. So 26, 29, 32, 34, etc. So your choice. You can get them, you can go to the graph. You can go to graph. Second trace gives you the calculate menu. We just want a value. And you can proceed to enter in each individual x value. It will give you the y prime value. Your calculator does not label it y prime. It just labels it y. It just sees it as a plain old linear equation. Other option, second graph, will give you your table. You can arrow down and find each y value you need for each x. So totally up to you, whichever way you'd like to do that. I'm going to go ahead and jot those down in our table. So if you don't have the information in your calculator, you can copy what I have here. I chose to round to the nearest hundredth just to be a little more precise. And again, those just come from your regression equation. You could also, if you wanted to, you could take the time to enter each one of those x values into the equation. That would take you quite a bit of time to do. So either use the graph in your calculator or use the table feature that's already there in your calculator. Make things a little bit easier. Now for the next couple pieces, let me show you something in your calculator that can make them easier. You're just subtracting the y minus y prime. You can enter each one of those if you want to. No big deal, there's only 7 of them. Your other option is to go to the calculator, go to Stat, Edit, and then in list 3, enter in your y prime values. Again, this is just an option. You can just flat out do the subtraction if you'd like. So again, I just entered all the y prime values into list 3. So list 1, 2, 3, those are the 3 columns I have in my table right now. All the x values list 1, y values list 2, y prime values list 3. The 4th column of my table says y minus y prime. So that means I want to take list 2, which is all my y values, minus list 3, which is all my y primes. So second L2 minus second L number 3, so it gives me L3. And it will give me the 4th column of my table. Do you have to do this? No, you can enter each one in, do just each individual subtraction on your own. Totally fine if you'd like to. I just did L2 minus L3 is all I did for that. Now some of you might be thinking, Miss Guy, it's just simpler for me to do subtracting each individual pair. That's totally fine. But let me show you why I chose this way. It makes the next column super fast. The next column then, it wants everything in list 4, but it wants it squared. So just go second number 4, gives you L4. And then just square it. So your list can make this table go really quick. And since we don't get a lot of data pairs anyway, none of your questions, I'm not going to give you like 50 data pairs to enter in or anything like that. You can do each individual data pair, do the subtracting, do the squaring, and it's okay. It's okay. The list can just make it faster for you is all. The list can just make it faster. And that's something too that, you know, if you're thinking, oh, I just need a little more practice with that, we can definitely look at that as you work on your practice. That's not a big deal. The last thing we need to do then is add up that last column. Now I know I wrote down a lot of decimal places there. Again, I'm just trying to be as accurate as I can. So what you can do, if you don't want to have to type all into your calculator and add it up, remember your calculator will do that for you. Your calculator will do. In order to get our calculator to do that, we just have to go to Stat and Calc, a feature we're all very, very familiar with, and just our one variable stats. But you have to tell the calculator L5. L5. You want L5, so second, number 5. If you have one of the TI-83 pluses and all you get on your screen is one var stats, you need to put L5 right after it before you press enter. Otherwise, it gives it to you for list 1. You might be thinking, Miss Scally, we don't need all of that stuff, though. You're right, we don't. We just need that summation of x. We just need that second item there. And I know they're not x values that we put in. That's y minus y prime, that quantity squared. But your calculator will just always spit it out as an x. No big deal. As long as you put list 5 in, we just want the sum. If that's bothering you, you can actually just add up all 7 values. Just trying to save you a little bit of work. And with a feature that you already know how to use. So we just want that summation of x. That's all we want. So that equals 187.408. So let's finish off our formula here. This value is our numerator. Sample size was 7. So 6.122 roughly. 6.122 roughly. Now, if maybe you didn't have your calculator with you, you didn't have the values already entered, or your regression equation, if anything that we did, any of those values, getting y prime, or getting your list to do the work for you for y minus y prime, or squaring that quantity, that's something I can definitely go through with you individually as you're doing your practice. If there's anything maybe I went too quickly through for you. Okay? Let me show you now. The calculator will do that standard error of estimate for you. I showed you some little shortcuts if you're feeling more comfortable at the table. Let me show you the calculator. Last time we saw, if we went to Stat, Tests, and we wanted F, Stat, Test, we wanted F, that linear regression t-test. That gave us our correlation coefficient, that gave us our linear regression equation. It would even put the linear regression equation into our y equals for us. It did a lot of the work for us. Let me show you what else it will do. So this is the same test we ran last time. We need the not equals. We need row not equals. And if we go to calculate, there's our t and p value we used last time with our hypothesis testing. There's our a and b that we used to write our regression equation. The s. Does it match? Is it pretty close? Yeah. We did some rounding with some things. Calculator's not going to do any rounding. So this s is your standard error of the estimate. It does not have the subscript est. So I don't want you thinking, oh yeah, great, that's easy. And then you get on the test, you're like, wait, well, Miss Golly, where do I find that standard error estimate again? I want you to use the calculator, absolutely. I show you the table process to just show you, here's what goes into it. And it is an option for you. None of the values in the table are tough to find. The table's time consuming. That's about it. So again, this doesn't have the subscript est. While we're on this menu, it also gives you your r squared, your coefficient of determination. So this one test, linear regression t-test, gives you almost every single value you possibly need for everything in this chapter. It does not give you critical values. It will not make the scatter plot for you. It will give you everything else. So do I highly encourage this one? Yes. That's why I showed it with sections 1 and 2, and now bringing it back again in section 3. Use this on your calculator. Please, please, please make life easy. Now, the last thing I need to show you, those of you that saw the calculator stuff, and now you're like, yep, okay, time to tune Miss Golly out because the calculator does everything. The calculator will not do the very last thing. The calculator will not do this. We have what's called a prediction interval. A prediction interval is similar to our confidence intervals that we've been working with the last few chapters. The prediction interval is for a specific x value, so a specific value of your independent variable. And we use it to predict, give us an interval, of where that actual y value would be for the dependent variable. That's what we're going for. the percent that we have, that's the percent of confidence that we have. So in this case, 95% prediction interval, we get to be 95% confident that our interval will contain the actual y value when we have x equals 30 assists. So our actual number of total points for our y when our x is 30 assists. Now, unfortunately, like I said, calculator won't do this for you, but it will give you all the key pieces you need. That's the nice thing. Step 1, I want to lay this out for you piece by piece. Here's some of the key elements we need to find. The calculator will do all of this for us. It will do everything for us. We want to add up all of our x values. We want to square all of our x values, then add them up. And we have x bar, which is just our sample mean. To get the calculator to do that, we just go to Stat, Calc, and our one variable stats. In this case, though, we need to switch gears. We need to go back to list 1, where our x values are. So second, number 1 for list 1. We need to go back to wherever your x values are. We need x values. Just be careful, the order I listed them out in isn't the order the calculator spits them out to you in. The order you put them down in on your paper doesn't matter. You just need to get those 3 key values down and make sure you get them in the right places on that confidence interval. That's all we have to worry about. So we had 234, 7,962, and x bar was 33.4. We need y prime. In order to get that, we put our x value into our regression equation. This was part I of our example. This was part I, so if you look right up above this, you see part J, right above that's part I. We also need the standard error of the estimate, and we just found that to be 6.122. These are all the key pieces we need. The calculator will do all that busy work for us. One variable stats for part 1. Our regression equation for part 2, we're using x equals 30. Standard error of the estimate, we just saw that our linear regression t-test gave us that standard error of the estimate. So all those pieces we have. But the calculator will not do for you. The calculator will not compute the values for you. And it's unfortunate. I hate when the calculator doesn't have the stuff, because the calculator does the busy work for you. And this one is a rather large formula. So on page 590, I'm not going to take the time to copy that whole formula back down here. So if you want to look at the formula as I put the pieces in, please open to page 590. Alright, so here we go. We start off with the standard error, y prime. Y prime minus t sub alpha over 2. That's the one thing I didn't list out at the beginning. T sub alpha over 2. You have a 95% confidence interval, which means alpha is at 0.05. So if you're using the calculator, you have to divide your alpha by 2. Degrees of freedom, n minus 2. If you're using the table F, use the row for two-tailed test. Keep alpha at 0.05. If you're using the calculator, the INVT, you need to use alpha 0.025. You need the alpha over 2. So we end up with t sub alpha over 2 is 2.571. Standard error of the estimate, 6.122. Then we have this whole big old radical. We have 1 plus 1 divided by sample size plus sample size times. You come across just a plain x. That's the x that you're given that you want the prediction interval for. So it's going to be 30 minus x bar. That whole quantity is squared, divided by sample size times the sum of x squared minus the sum of all of our x's, that quantity squared. In between the inequalities, you have just a plain old y. Y is our actual value. So if x is 30, our actual y, what should it be? That's what we're trying to predict. Now, I don't know about you, I don't feel like rewriting that whole entire other side again. So I'm just going to write enough to show you the difference between the two sides. Same as our confidence intervals have been. Subtraction on the left, addition on the right. If you go through, you do the computation piece, what you should get, 44.128. So what we are saying is that when our x value is 30, so when we have 30 assists, we are predicting that our actual y value, our actual total number of points, is somewhere between 44.128 and 78.978. Now, again, finding the interval is one thing, the explanation piece is a big part of it. With this interval, we're saying we are 95% confident the interval contains the actual value of y, which is our total points, when x equals 30, and that's our assists. Just wanted to leave it kind of generic in there, and then make our labels in the parentheses so it's specific to the example. That's what this prediction interval is representing for us.